of data, how can you make some sense, make a sense of this data? So you need a statistical device that gives you a function, that gives you some parameters so that you can interpret and you can read because we are limited. We cannot process information that we get from a large amount of data. Okay, so this is what. So if we have something so compact like a line that tells me yes, with some error, but correct on average, right on average, can represent all this data, then I prefer to use this instead of having all these points that don't really tell me anything, and that don't allow me to make comparisons or to predict something, okay? Because what I told you before, concerning, for example, 12 is never observed, which is the temperature. But if instead I want to know what I should expect if I have a temperature of 12, then I can predict it. Because I have my line. Then I know that there is some error, but roughly, on average, it should be correct. Okay? So, how do we calculate these parameters, alpha and beta? The most used technique is the ordinary least square method, the method of least squares, that requires that the sum of the residuals square, or the square of the residuals is as small as possible. So, alpha and beta are chosen in a way that minimize the square, the sum of the squares. Guys, this doesn't need to scare you, because for this ordinary least square, for this least square method, there is a formula to calculate alpha and beta. So you don't need to compute this to make maximization, minimization, and other things. Okay, there is a compact formula to calculate alpha and beta. This isn't true with other techniques, necessarily with other techniques, but it is true with the OLS. Okay, the ordinary least square, the least square method. So I say ordinary least square because in the box you usually find OLS. OLS means ordinary least squares. That is what we are talking about, okay? So the formula to calculate beta and alpha are these. Very simple. Look, I is the index of the observations. N is the maximum number of observations, so you have to go from 1 to n and sum the x's, the difference between the x's and the mean of the x's, times the difference between the y's and the mean of the y's, divided by the square differences, the sum of the square differences of the x's. So given your data, if you compute this, you obtain the estimator of the slope of that line. Okay? So this is the ordinary least square estimate of beta. To calculate alpha, alpha is once you know beta hat, mean of the y's minus beta hat times mean of the x's, and you get your estimate of alpha. Okay? So for the gas consumption, if you use the formula, you get beta equal to minus line. Look, you expect the beta to be negative because the line has a negative slope. So you have to expect beta, that is the slope coefficient, to be negative, and a positive intercept the alpha, because remember the data are like that, and there is a positive intercept. So the positive intercept is 222.5. So this is the relationship, the line that approximate the data that we have seen in that graph. And this equation could be used as a tool for predicting gas consumption for any given temperature. Okay, even if we don't observe the y corresponding to a certain x, but we can predict it using this equation. Guys, prediction is extremely important for your coursework. Okay? So, here there is another data set, and in which there is household final consumption expenditure and household disposable income. So if we want to approximate the final consumption expenditure through a line against the household disposable income, we can use the same technique. So we can fit a line through this data. What's happening? We can fit a line through this data, and we can compute alpha and beta. See, as simple as that. There are software, even freely available on the internet, in which you put the data and you get alpha and beta. Okay? Guys, we will see exercises about this and how to interpret the regression coefficient.